All right. I already see some people coming in. Welcome, everyone. My name is Sergi. I'm really happy to be here the first day of ICLR. And we're super lucky to have three authors of three super interesting papers at ICLR that we have recently highlighted. So shall we start with some introductions, Jakub?
Yeah, so I'm the founder of Zeta Alpha. I've been in AI for like 30 years now, and still keeps me passionate. And I have a kind of personal love story with iClear because actually the idea for Zeta Alpha was born at iClear in New Orleans 3 years ago, and there hasn't been a physical conference since then, which is a bit of a itch I'm waiting to scratch.
Yeah, I have also very fond memories of the previous iClear editions, although I haven't been lucky enough to attend any physical in-person one. So I really hope that I can do that next year. So with that, we also have three authors of various papers at the conference. First of all, Anirudh, Goyal, wanna introduce yourself?
Hello. Thanks everyone for joining. I'm Anirudh Goyal. I'm a PhD student advised by Professor Yash Benchio. My current kind of research interests center around understanding how neural networks can compose and abstract their own representations in a way that can be used to generalize the new samples or new tasks. Thank you.
If we have to, if you would have to make a fourth guess, would you consider yourself more of a computer scientist or more a cognitive scientist?
I consider myself a computer scientist.
All right.
Cool. Yeah, I think that the line of work that you're working on is super interesting, and I think that last year we already highlighted the RIMS paper, I think, or was that on NeurIPS? I don't remember, but I think that was also some work that you did that was super interesting. Next up, we also have Samira Abnar. Where are you joining us from?
Hi, everyone. Yeah, so I'm Samira. I'm in Amsterdam currently. I'm a machine learning researcher at Apple. And I've done my PhD at the University of Amsterdam. And my background, my PhD work was around inductive biases, natural language, language modeling, and these kind of things. And currently my focus is around reasoning and out of distribution generalization.
That's super interesting. And we're going to be commenting on a paper about large scale pre-training that I think you worked on some time ago when you were at Google.
Yeah, so last year I was doing an internship at Google Brain. I was working with a team of researchers in Google Mountain View and in Amsterdam. And the work is this paper, the outcome is like this paper exploring the limits of large scale pre-training, which, yeah, we're going to talk about.
And did that work also end up in your PhD thesis?
No, actually, no, it didn't.
We'll dive into that in a bit. And finally, we also have Rose. Who can you introduce yourself?
Yeah, sure. So I'm Rose. I'm a second-year PhD student working with Noah Goodman, and broadly, I'm really interested in multi-agent systems, interaction, and self-supervised learning.
And I saw on your webpage that you have a background in robotics, actually, from earlier days.
Yeah, I first started doing research in undergrad in robotics and reinforcement learning, which had broadly gotten me interested in a lot of different problems in the multi-agent space before exploring some other paths when I moved to Stanford.
I'm really curious to hear, when we talk about your paper, how the multi-agent interests in your paper come together.
Yeah, definitely. Yeah.
All right. So shall we dive into the content, Jakub? I know that you.
Before we move to iClear, I just want to, as always in this webinar, just pick out some highlights of AI news or gossip for that matter. So one really big hooray for the local Amsterdam AI community. I don't know how local it really is, because they're, I think, in London headquartered. But Benevolent AI was listed on the Amsterdam stock market today. Yeah, that's a pretty exciting company working on drug discovery. And yeah, it's really nice to see AI coming so close to applications and actually having an impact on the real world. I think they're working actually in parallel on 20 different medicines for various diseases. And I think there's a connection to one of the keynotes, but we'll come to that. In another piece of European AI news, there was, of course, we have already GPT-3 and Cohere and AI-21, all these big language models as a service that you can purchase. Now Europe has one of its own. The German startup company Aleph Alpha. We share one word in our company names, but they're a bit further ahead. And they just launched a little bit less than 2 weeks ago a multilingual, multimodal model. And I think, Rose, you graduated in Germany, so you can read this, right? I saw it.
Yeah, I can.
That you have a German Abitur. Yeah, German, big economic power in Europe, also working on their AI autonomy. And in this sort of geopolitical struggle of AI progress, 2 weeks ago when we had our previous webinar, we reported on this paper a roadmap for big model, and sort of the Chinese answer to the foundational models paper from Stanford. I think, Rose, you actually co-wrote some of that as well. So this is the Chinese answer to that, but just as it dropped onto archive, Twitter quickly found the issue with it. And in fact, there's a big heated discussion that exploded that parts of it were literally copied from other people's papers. So, well, it's a 200-page thing, so accidents can happen. But maybe it was written by one of these Chinese big language models and it just memorized the training data. Who knows? It's being repaired. Beijing Academy of AI offered some apologies and being repaired. All right, so let's dive into ICLR. For sure, the main news of this week. So the conference has already started, in fact, in kind of US midnight time. And the first keynote has already been delivered. So the conference is going to run for the whole week, only virtual. So it's fully in this online environment with pre-recorded talks, poster sessions in Gathertown, and I think also some Zoom sessions for interactive stuff. Gonna run kind of 24 hours per day, Monday, Tuesday, Wednesday, and Thursday. And then Friday, when we're already all exhausted, there's another onslaught of 19 workshops that run in parallel until, for Europeans, deep in the night. So that's kind of the general outline. What do you guys think of it being purely virtual? Should they have gone kind of hybrid, or do you think that virtual is fine given all the sort of CO2 and flight shame and climate change issues? Samira, what do you think?
I guess, I mean, probably if we can manage to do things efficiently in a hybrid mode, I guess that would be perfect. But I like this kind of virtual style because it makes it a bit more accessible. I mean, it's like this climate issue stuff, but also some people it was always a problem for some people who, for visa issues, for example, couldn't attend the conference, or for funding issues, they didn't have enough money to pay for the flights and stuff like that. So that's nice that there is an option to attend these conferences online. But I really miss like the personal, you know, running through the corridors of a venue, trying to find people, talk to them in person. Yeah, I really miss that too.
I think
Rose,
one of the
what do you think? So you're a second year PhD student. Have you ever been to a real conference actually?
Yeah, not really. Last year I did get the opportunity to go to EMNLP in person, which I was very grateful
Oh,
for.
nice. Yep.
But you know, I think it would be really great, of course, like as a younger PhD student, to be able to meet many many new peers around the world. I definitely agree with what Samira was saying. It makes everything really accessible. You know, you don't have to pay for thousands of dollars for a flight plus hotels. And so there's a lot less financial burden, but I think everyone sort of is also itching for in-person interaction. So having an in-person conference, I think, would just definitely increase a lot of the engagement and in-person, just like, meeting new people. So
I want to add to that. I feel like one of the big problems with the virtual problems that I found myself is that no one is attending full-time an online conference, right? Everyone is kind of juggling work, and because, you know, you can just switch tabs. And I feel like the first time I went to ICLR, I was actually full-time attending ICLR as a student, and that was great. But then the next year I was kind of half going, but then solving some work stuff, and you know, the fact that you're not 100% there is kind of this thing that makes it worse.
Yeah, but the good thing is that everything is recorded and you can watch it later. So I didn't have time. I had to do some other stuff for work this morning, and I didn't get the chance to see the first keynote, but I'm going to watch it later. So I hope we keep that, because I really hate that when you're running around this like big expo center trying to find the right room, and then you're too late and you missed it and it's gone. So definitely some benefits there. And I think the fact that it's accessible for everybody from globally is a really big plus that we shouldn't lose. So before we dive into the papers and the content, just for those of you who haven't heard about us, we're Zeta Alpha. We're a startup from Amsterdam, working on neural search and recommendations, and applying that to the field that we love most, our own field. So we're building a platform for AI and data science teams, especially in industry, to discover and organize knowledge from archive, from conferences, from company blogs, news, GitHub, social signals from Twitter, really everything about AI and data science that we'd like to know. And part of that is the platform, and another part of it are these webinars and Sergi's blogs, where we try to also kind of digest it and make it accessible to people. And the platform itself allows you to not only discover things, but also to organize them in collections of papers and notes, share them with your colleagues, and based on this sort of curation and organization that you do for your personal interests, we get to know what you're interested in, and we can send you pretty decent recommendations. So that's the short commercial pitch there. I will stop now. Well, I will never stop, because as a startup, you're always selling. But let's dive into the paper. So what's a good way to kind of discover and organize when there's almost 1,100 papers, right? And the volume is growing every year. I think last year there were like 700 in ICLR. Year before that 600, something like that.
800, yeah. I think it hasn't peaked, or at least this is the most yet.
This is a world record, and yeah, there's a like going through the program, I found it very hard to navigate. And of course, there's like the highlights, the keynotes. So I'd like to know from our guest panelists, which ones are you most looking forward to?
I was planning to attend. I think it's this evening. Bin Kim's talk. That should be pretty interesting. Yeah, and I'm a big fan of Doina Pickup as well. So I'm gonna attend whatever talk he has.
Whatever she's talking about. Yeah, it's about the path from reinforcement learning towards general AI, I think.
Yeah, I think so.
Rose, what about you?
Yeah, I saw a part of Bin Kim's, I think she pre-recorded her talk already. So yesterday I was taking a look at that. So I wanted to like finish watching it. And yeah, I thought I was really curious about what Kunle had to say, because I know that he's a PE professor here at Stanford, and might browse around some other talks as well.
Yeah, he's working on like new architectures for making deep learning, like hardware architectures for making deep learning more scalable and energy efficient, right? Yeah, super cool
Yeah.
work. What about you, Anirudh?
I think probably the most interesting part for me is the ICLR keynotes, just because we get to know certain speakers whom we would have not known otherwise. For example, I don't think I'd know any of the other people who are not related to machine learning, like Kunle Olukotun or someone, as well as John Amasi, I think. So I like keynotes, like all the keynotes.
Yeah, so John Amasi is, I think, one of the least machinery. He's actually a healthcare researcher from Africa, and he's gonna highlight, I think, the sort of the challenges related to neglected diseases that pharma has typically not been focused on, and I think he should really he would have benefited from directly connecting to Pushmeet, and because DeepMind is obviously working on some of those things, and Pushmeet really has his fingers all over every sort of headline grabbing DeepMind paper that has come out in the last year. So it's really kind of the challenge in terms of pharma and life sciences research, and maybe the solution. What about you, Sergi?
Yeah, I heard also excellent praise of Ben Kim's talk. So I actually started watching it before the webinar, but I didn't get to finish it. But it seemed really interesting so far. So I plan on watching that definitely.
All right. Another way of navigating the program is, of course, to see what the reviewers thought were the best papers. Typically, from an industry perspective, we tend to think that these reviewer-selected best papers are, of course, academically excellent, but sometimes a little bit theoretical. So actually, our overlap Sergi, the overlap with your list,
I think it's with the
one, right?
Yeah, I think it's with the Bootstrap meta learning. We also highlighted that, but the other works I also skimmed through those. But I agree with you that they are quite more theoretically oriented. And
of course, ICLR is the conference on the theory of learning representation, so you can hardly blame them, right?
No, absolutely. But if we're trying to make them a little bit approachable from a broader audience, that's harder.
Any favorites that you guys have in this list? The ones that you definitely want to catch?
there is this one efficiently modeling long sequences with structured state spaces. This one is actually on my reading list for a long time, but I haven't managed to read below the abstract.
I have to admit the same, and I think it's actually also, I suspect it's related to Rose, her paper, right?
Yeah, it's also pretty related to just trying to do better long horizon generation. Yeah.
Have you read it in detail, this one?
Yeah. So I think Albert had presented it internally a few times, and there's also this pretty good sort of tutorial or walkthrough, I think, written by Sasha Rush and Sid Karmchedi, just to give you sort of more hands-on feel of S4. So definitely check that out if you want to sort of get a better understanding of the paper.
Cool. Right, so we got actually, I think Sasha built this stuff. ICLR was kind of one of the first online conferences in right after the pandemic started, and in like an amazing time they built this whole environment for virtual conference, which I think is still used exactly in the same form today. It's like write once, don't touch the code ever. And one of the really inspiring aspects of this was this, that every paper has an embedding, and there's kind of a Disney plot or two-dimensional mapping, like this semantic map that we have all been, well, at least I have been dreaming of since the early 90s. My master's thesis was about semantic neural maps. But anyway, we thought that's really cool, but it's kind of hard to understand what you're looking at. So in fact, we have taken this as the inspiration for a part of our own functionality. And we have built this kind of similar themed exploration interface in Zeta Alpha, where you can explore all 1,000 papers kind of at the same time in one visual overview. I just want to go there for a second and drop out of the presentation. Let's see if I can do that live demo. So basically I have here, somehow we're missing one paper, Sergi. It's 1,095 accepted papers, but maybe one of them doesn't have a correct PDF or something went wrong. But we have almost all of them. Here's this visualization, and you can kind of, it's based on the neural embeddings for each paper. And then we calculate on the fly similarity matrix between the papers. And you can kind of really nicely zoom through this space and explore, you know, what papers are related and connected by their semantics. And you actually see very nicely that there are some areas which are less connected to the rest in the program. So these red dots here, that's the reinforcement learning guys. They've never been really connected, and they're kind of breaking off, I think. But let's hope that that they can be kept in ICLR for many years to come, because there's a lot of interesting stuff going on there. This little area here is all the graph neural network stuff, also kind of a tightly knit religious community. Anirudh, you've also been working with graph neural nets, right?
Right.
So do you have a good overview of what's on at ICLR this year in GNNs?
I think people have been doing like all sorts of improvements, like improving upon how we can learn the underlying graph structure. For example, one thing is GNN assumes that the information of the nodes is given, but for kind of agents interacting, the only observables they have is kind of low-level visual information. So how do you construct these high-level variables, as well as improving upon message passing? Like normally the message passing algorithms are like every node kind of interacts with every other node. So how can you interact? How can you improve upon kind of how to create synchronization among different nodes, and as well as using these GNNs for many various different applications or various different kind of community specific problems.
Yeah, and of course, we mentioned drug discovery already is one of the main applications, which is really taking off. We have this Max Welling lab in Amsterdam, which is making some waves there as well. Here is kind of the natural language field. So that's the one that's my favorite. I'm gonna scoop around there mainly. So it's hard to do that in 1 minute. So just to give you kind of an overview, let's dive back into the slideshow. So one other aspect that we have been kind of exploring to make sense of the program is the fact that actually conferences no longer have scoops, right? It's a really kind of an archival function almost. Everybody has put their paper on archive already months ago. Well, most people have. And you can see that by the time of the conference, actually, some of the conference papers are already kind of famous and they have gotten lots of citations. Usually that's also kind of a function of how long the authors have been pushing the idea, and some of these papers actually came out on archive almost a year ago or something. So also some interesting papers in this list. I think did fine-tuned language models are zero, that's a FLAN paper, right, Sergi?
Yeah.
Did it make it onto your list, or did you drop it? It was too established already.
Yeah, it was originally, and then we decided to swap it for Rose's paper because we already highlighted that before, and we wanted to put something different.
And Samira's paper is there. Hey, in the top 10, already famous. Well, I think it's already had a lot of influence. So let's dive into the actual top 10 papers. For those of you who want to read up on it and get all the full details and the links to the code and all of Sergi's comments, the blog is on our paper. I think by now we have around 1,000 people already read it. So Sergi, what do you want to start with?
Sure. I think we're planning on starting with Samira's paper on the exploring the, I think it's on the next slide. Yeah, exploring the limits of large-scale pre-training. So I think this is a paper that was first published on November or something. We talked about it briefly previously, and I thought it was super interesting because in this sort of changing paradigm where most people don't train end-to-end models, but kind of use one pre-trained model to train on whatever downstream tasks they're using. So this is a paper that systematically studies that. So I found that super interesting and useful for people to look into that. That said, Samira, do you want to give us a short summary of this work that you did?
Sure, yeah. So like here we study the effect of scaling up with respect to these 3 scaling parameters of data set size, model size, and compute on a performance of a pre-trained model on a set of downstream tasks through the lens of upstream performance. So we basically integrate all these factors into one and measure it through upstream performance. And we show that then the relationship between the downstream and upstream tasks is not linear. And as we improve the performance on the upstream task through scaling up or tuning hyperparameters, eventually sooner or later, the performance on the downstream task saturates. When it saturates and at what value, it would depend on the relationship between the downstream and upstream accuracy. We show some evidence for that in the paper. And basically the take-home messages are, maybe the most important ones are like, first, there is no free lunch. We don't get one checkpoint that is a solution for everything just by blindly scaling up. And then that second, we have to maybe not forget about this 4th scaling parameter, which is data diversity, if we want to get improvement on a wide range of downstream tasks.
Mm-hmm. So if I'm not mistaken, this is all done on computer vision tasks, right?
Yes, yeah, that's true.
So one of the things that I found interesting when the first time I read the paper was here all of the upstream performance or you use the term pre-training. If you come from an NLP background, you often are gonna assume that pre-training means self-supervised pre-training or something like that. But in this paper, you are using labeled data all along, right? In the upstream performance and in the downstream performance, right?
Yeah.
So do you think that these? So I guess my question is, how much do you think these findings correlate with stuff like self-supervised pre-training on computer vision, and then in other modalities like on text, and all of that?
I think like the core observations are going to be consistent, but the thing is that so first of all, we are looking into the performance of the task setup is image recognition, like image classification, but we are working with super large data sets, at least on the pre-training side. And then the number of classes is like, I think for JFD, we had like 18,000 classes. So that's a lot. So it can just increasing the number of classes, I think could, if we had only, for example, 10 classes, the way that the model would work would be different. But I think I have this, I don't know, I'm not sure about this because you have to test this empirically, but I think as we improve the number of classes, this difference between self-supervised and supervised in terms of classification would probably fade away a bit. But I mean, if you think about this intuitively, the thing is that you are using these models to extract features from data. And it's in both in language modeling for both and image recognition or any other modality. And the reason that this saturation happens is that these features for different tasks are not necessary. So you need to basically view the data and select different features based on different tasks. And you get improvements on downstream tasks as long as the features that you're picking up are relevant. And as you abstract away from low-level features to high-level features, that would be more tricky. Now for NLP, we have data diversity a bit more than computer vision by default, maybe in our data sets. So if we just run this empirical analysis on data that we have and don't take into account the conditions under which maybe we would observe some differences, but I think conceptually they're not so different.
Mm-hmm. I see. So another thing that I found I would like to ask you about is the architectures, right? So I think that you experiment with three main architectures for vision: transformers, VITs, then ResNet and MLP mixers, right? Yeah. And I think this came at a time as well where I feel like in the past year there's been a lot of works kind of training these different architectures very successfully on ImageNet and other image classification datasets. So first, is there any interesting difference in quality in the behavior of these different architectures? And secondly, like what is your opinion on which ones of these architectures is gonna kind of stay in the longer term?
So it's kind of a tricky question, but the point is that I guess one thing that I learned from this study is that if you tune things properly, you can have best performing model anything. Like ResNets can achieve state of the art as well as transformers and MLP mixers. And there are some, I mean, if you think about it theoretically, sometimes these models can be different in terms of expressivity. For example, transformers and MLP mixers, transformers are definitely more expressive than MLP mixers, at least some versions of them. But since our benchmarks are like, you don't need like a super expressive model also to solve these benchmarks. So yeah, as long as we figure out properly how to tune the hyperparameters of these models, they're all gonna perform equally well. At least that's what I think. But I mean, I think they differ in terms of how easy it is to train them and how easy they scale up. And yeah.
I guess maybe Anirudh, this kind of relates to the work that you've been doing. My feeling after seeing all of these papers is that, like you're saying, as long as you're kind of benchmarking within distribution, sort of any network, like you can make any large enough network learn the right patterns. But as soon as you want to get some robustness out of distribution, generalization, efficient learning, all of this kind of stuff, then all of these sort of inductive biases come into, become more important or something like that.
Yeah, that's true. But then also, I mean, that's also this, you can also think about it in terms of this data axis. So if you have a model with a lot of inductive biases, that would perform better, that would be closer to like this Pareto frontier, or like this convex hull line that we have here. When the size of data set or the number of training iterations is smaller. But as soon as we increase the data set size or like the compute that we have in both of them, also models that have less inductive biases, they are able to catch up, and they can become a bit better because there are less constraints. So with fewer number of parameters, they can be more flexible and adapt better to the data.
I think that's fascinating, and I really enjoyed this paper, and to everyone watching, I really highly recommend that you also check it out.
I'm just curious, what is the total amount of experiments that you run here?
That's a good point. So like, we did not train these models ourselves. These are the models that researchers from the different teams have been training to basically get to the state-of-the-art results and these data sets. And we just had access to a collection of these models, so we just pulled them off and plotted them basically. So that's yeah. So that was the fun part.
So in terms of CO2 impact, you're on the good side. It's much less expensive experiment than we might think, and much less expensive than 5,000 people flying to New Orleans or something like that.
Yeah, yeah. So part of the experiments we tried to replicate. So see, for example, this plot on the right side, I think this one with the, I don't know how to, like, this one are the experiments that we run, but these plots on the left, that includes around like 5K experiments. Those we didn't train ourselves for this.
Good reuse.
Yeah.
So shall we jump into the next paper?
Yeah, that's a Rose paper, and I have to congratulate you. It's a very nice paper to read, and also the fact that as a second-year PhD student, you already have a kind of oral presentation at ICLR. I think that's like kudos, very well done. Can you kind of explain the main idea of the paper and how you solve that?
Yeah, sure. So I guess broadly speaking, the paper's really interested in just this very difficult challenge of how do you generate long sequences. In particular, here we're studying long sequences of text, so in the language domain. And so sort of intuitively speaking, for our method, what we want to enable these language models to generate long coherent texts. But generally when we prompt them, at least when I was like playing around with GPT-3, what would happen is that they would start off generating pretty coherent texts at the beginning, but then as you sort of push the length of a desired text to become longer and longer, you start to see that they meander or generating just completely incoherent text results. So what we basically did was we want to capture coherent text as almost like a smooth latent trajectory. And we played a little bit around with different ideas, but the one that we sort of converged to is using a Brownian bridge model as our target latent space. And so that is what is depicted in figure 1, where a Brownian bridge model is defined by two points, so a start and end point, and any point in the middle is sort of considered a linear interpolation between the two, with stochasticity depending on your relative time position between the start and the end point.
And is the start is like the sort of the prompt, the first sentence, and then the end could be any sentence kind of further downstream.
Yeah, so all of these latents are supposed to capture sort of features on the sentence level of text, so not on the token level, which was a common question that we got as well.
Yeah, but it doesn't necessarily have to be like the first and the last sentence. It could be any sort of sequence in between.
Right, yeah. So definitely one extension of this idea is you do multi-point conditioning. So you don't consider this model as strictly just the first and the last sentence of a text, but you can imagine, there are certain sections that you want to hit. So you encode an endpoint for each of those sections or for each of those desired target points. And then you interpolate in between. So you first take like Z0 and then Z1 as your start and end points. And then once you finish generation to Z1, you change from Z1 to Z2, condition, generate a path, and then decode. So these are all things that can be sort of written in closed form using the model, and then just out of the box used for decoding.
And any special tricks you have to do to make that work at the inference time?
I guess not. Nothing that I can really recall. The nice thing, I guess, about the method is that it is you are sampling from a stochastic process, so there is stochasticity in the embedding path. So like when it comes down to sample diversity, it does help a bit, although there is already a lot of stochasticity in language models, since we are sampling from a probability distribution or some truncated form of a probability distribution. So the text samples that you are getting are relatively diverse. I don't think that there were any explicit tricks that we used for doing generation. It was really just, it was pretty straightforward. It was generate a latent plan, decode from it, and then you can sort of apply different coherence metrics to see whether or not there were any improvements in generation quality.
And so the code is online. Also applause for that, by the way. In the code, you actually it's based on GPT-2 models, right? So I'm curious, like, what are your thoughts on to what extent the somewhat smaller GPT-2 models have a lot more of this choppy behavior, and isn't scale by itself somehow already a method to fix it when you go to like GPT-3 or even larger models like the recent Pathways language model seems to get a lot of this kind of sort of global coherence just from the scale alone. What are your thoughts on that?
Yeah, I think that with larger models, so higher model capacity, and with pre-training on a lot more data, I think your priors, so the models that the priors that the language models learn are pretty strong. So I could imagine transferring the same experiments to GPT-3 model, and maybe the incoherence issues aren't as strong. But that being said, I think there's sort of two problems. It's almost like a chicken and egg problem, which is one, in NLP, people haven't really settled quite much, or don't have a a strict set of metrics to measure coherence in text. In particular, what does it mean to generate a long coherent sequence of text? And so that is sort of problematic, where a lot of it is very qualitative, where you read it and then determine for yourself whether or not it's coherent. And I guess the other thing is that I still do think that when it comes to generating either a coherent text sequence or image sequence, or like a video, at the end of the day, it should incorporate still some form of goal conditioning, which is sort of the main push of our paper. And so even though you might sample pretty reasonable text, and maybe it might sound better with GPT-3 than GPT-2, I do think that in order to really measure whether or not the model is generating something that you would want to see, it should incorporate some form of goal conditioning, some form of like, there is a target that you are trying to express. And so, if we have a metric of how much it's deviating away from that specification, that would be really nice. But I don't think we really have a robust set of metrics for really building up that toolbox.
Yeah, I think that's a very good point, that this goal directedness kind of comes for free with this approach. Can you see also like extensions towards other ways of controlling the generative models, like let's say if you imagine for criteria like safety or understandability or things like that?
So I'm definitely not an expert in I guess thinking about language model objectives for tuning for specific desiderata. So like, what does it mean to even generate safe text? I'm definitely not an expert in that. And I'm sure there are a lot of other people who have more to say on that.
When it's unsafe, you see it.
But I think just thinking about the way that we want to do pre-training, the way that we want to do fine-tuning, I'm sure that there are a lot of people out there who have specifically worked on this and have more insider advice. But I think in general, being able to interact with models the way that we almost interact with humans, I think is definitely something that is very much on my mind. So what are the kinds of interfaces that let us expose those desirable features? It would be, I think that is definitely one big push that I'd like to pursue in my research career. So be that either through, integrating these kinds of implicit structures that we think language is built off of, or in other domains, like in reinforcement learning. So being able to better express goals as opposed to just giving sort of a simple goal image to a robot and saying like, this is what I want you to accomplish. There's a lot of ambiguity because that is a very underspecified way to express a goal, which humans don't really sort of rely on. Like they generally reduce ambiguity before executing or before making decisions. So there are a lot of interesting questions when we think about improving interaction between a model and a human, and what that ultimately means downstream for a model's performance when we reduce that ambiguity through interaction.
Great. So I think we have to move on, but like any good paper, it raises more questions than it answers. And that's really great. So thank you. I think we have to, looking at the clock, move on to...
I want to have a bit of time to talk about this. Coordination among neural models through a shared global workspace. I really like this paper, and I think it kind of belongs to this whole family of works that experiment with taking inspiration from neuroscience, and also introducing these sort of bottlenecks that aim at making models more robust in out of distribution, generalization, and these kind of things.
So old school cognitive science, like Marvin Minsky was nice.
So Anirudh, do you want to explain what you guys did with this paper?
Right. So if you think about the past 4 or 5 years, like deep learning has kind of seen a movement away from representing examples with kind of monolithic hidden states, like in MLPs, towards a richly structured state space. For example, transformers seems to segment information by position. Object-centric architectures, they try to decompose information about images into entities. Graph neural networks tries to incorporate information in these nodes. And in all these architectures, interactions between different elements are modeled via pairwise interactions. For example, transformers make use of self-attention to incorporate information from other positions, and object-centric architectures as well as graph neural networks, they kind of make use of message passing or pairwise interactions again to model interactions among different entities. So the basic promise or basic question which we were raising was, we consider how we can improve on pairwise interactions in terms of global coordination in order to kind of build a coherent integrated representation that can be used for downstream tasks. And the basic idea was simple, that the proposed method includes a kind of a shared bottleneck through which communication among different specialists or different components take place, but there are limits on the communication bandwidth, and different modules or different specialists needs to compete for it for access. And we show that such kind of a capacity limitations has a rational basis in that they encourage specialization and compositionality among different constituent elements, and they also facilitate the synchronization of otherwise independent specialists. That was kind of a two-line summary.
So could you? So I think that intuitively it makes a lot of sense that introducing these kind of bottlenecks would force the network to learn more, compositionality and those kind of things. So can you sort of explain what kind of tasks these sort of architecture you would expect it to excel at?
So it was not a specific thing. For example, the basic idea was like in all the transformers, slot-based architecture, or GNNs, we make use of pairwise interactions. And the idea was to come up with a different way of incorporating interactions between different constituent elements. And we experiment with all these different architectures like normal or vanilla transformers, as well as graph neural networks, as well as slot-based architectures, in which we replace pairwise interactions via this bottleneck, such that interactions between different elements happens through this kind of a shared common communication channel. And yeah.
So something that I feel like happens a little bit in the research communities, like a lot of the things that these models sort of are good at, or out of distribution benchmarking type of things, seem to not grab the attention of people that all that much. Like you wouldn't see a headline, saying, this out of distribution or something like that. I don't know. I guess my question is, how do you get more people excited about these, or how do you kind of shift the sort of a lot of the benchmarking to be in these sort of settings where these sort of architectures start to become more relevant? I don't know if that makes sense. But...
Right. I guess it's probably a more broad-ended question, and I don't know what the exact answer is. But one thing is, maybe there's not really a kind of a benchmark which specifically measures what really is out of distribution. For example, out of distribution could mean different things for different people or different problems, as well as different kind of communities. And for example, in Vision, we have kind of an image net, and there's no such thing. There's no such kind of a common way to estimate how we measure performance on out of distribution samples. And maybe one of the reasons is like most of the theory in kind of machine learning kind of based on the premise of IIT samples that from training and test, they're kind of drawn from the same distribution. And maybe we don't have a good handle as of now how we can get a kind of theoretical hold of how to even define outer distribution. Some people have certain good ideas. So that's why I think different people, including myself, try to create OD samples and try to measure accuracy on those OD samples. One such thing in which it is useful is kind of compositional generalization. For example, if I show you different concepts during training time, and if I ask you to reason about compositions of different elements different from the training time, as humans, you're able to easily figure out the novel compositions of the same training task or same training concepts, even though these concepts or the new training sample has kind of 0% probability under the training distribution. So among the kind of an outer distribution, kind of a broad problem, one such problem which kind of excites me is compositional generalization, where we can reuse, recompose information about the past concepts in order to reason in kind of a systematic and compositional way.
Mm-hmm.
I would argue that you are much more of a cognitive scientist than a computer scientist than you are prepared to admit, Anirudh. That's a compliment, by the way.
So, Samira, you mentioned that your research interests are somewhat overlap with this. Do you have any comments on this whole topic as well? You're mute.
Yeah, so I think that these are all super interesting, and basically I have one question I'm gonna ask. This is something that I have been thinking about. So we think about in terms of like these architectural changes that we can incorporate into the models to make them more compositional, or make them do a bit more, be able to do a bit more complicated reasoning so that they can generalize to on different tasks, or be a bit more dynamic in some sense, or have some proper inductive biases. And I always ask myself, would this change, would this modification that I'm applying at this model architecture or the new architecture that we're coming up with, is it able to do something that the standard existing, for example, like a feed-forward model, or feed-forward models are too simple, like MLPs are too simple, but transformers are not. They have some form of conditioning and all that. And I always ask myself, are they not able to implement this given we properly train them? And so I'm in favor of, moving toward like a more unified framework or model that we can apply everything, apply it on everything. This is basically kind of the challenge that I try to think about, and I want to know what you think about as well. That
it's a really interesting question, something which I think about myself, because one thing is like you can fool yourself like very easily into thinking that the thing which you're proposing is doing something different. And one way which I kind of try to debug is try to understand what the network is learning. To just give you a bit more kind of a concrete example, for the paper, we took a very simple task like MNIST classification, in which you have 28 cross 28 pixels, and that there are some white pixels, some black pixels, and white pixels represent some sort of a digit like 0 to 9. And here the idea was not to figure out what accuracy on the training or test setup we are getting, but just try to analyze what the network is actually learning. So one thing is like everything was same, like the training accuracy was the same between the proposed method and what we are doing, but the solution which was learned was very different. For example, in transformers, we are not able to figure out any semantic separation between the foreground and background, that there are certain layers which are focusing on background information and the certain layers which are focusing on foreground information. But for our work in which we pass different elements through a shared bottleneck, one such difference was we were able to, at some higher layers, we were able to figure out some sort of semantically separate concepts. That is, there are certain positions which are focusing on the foreground information, and the certain positions which are focusing on only on the background position. So during test time, if you have to change one of the foreground or the background, you can apply an intervention during test time such that the rest of your network kind of doesn't really change. So that was a kind of an interesting insight for me as to see how the learned solution is different as compared to your method and the baseline, as compared to relying on kind of a downstream numbers, whether it's a training accuracy, whether it's a test accuracy, whether it's outward distribution accuracy.
That's super
So
interesting.
I hesitate to cut off such an interesting discussion, but it's 4 o'clock in Amsterdam, and we're running at the end of our time. Just gonna really quickly shout out the other papers on Sergi's list. We're a big fan of Perceiver and all its evolutions. It's a really fascinating architecture, so check out Perceiver.io. This is a paper about also cognitively plausible continual learning method. We have a paper on the list about non-episodic benchmarks for reinforcement learning, interesting development in graph neural networks, bootstrap meta layering, also one of the best paper awards, and another sort of Amsterdamish flavored production, very interesting new paper, autoregressive diffusion models, a paper on poisoning and backdooring contrastive learning, which shows that just a few images that are planted somewhere on the internet, if they're harvested to train models like CLIP, they can fool them into misclassifying or even systematically misclassifying classes of images. And that's it. And the rest you will have to read on Sergi's blog. Any last words you want to add, Sergi? No, not really. Go read it. And yeah, I wanted to say thank you to the authors, especially because you know, it was super interesting to have you on and to be able to ask you questions about your work. Yeah, thank you so much for joining us. And one last shout out then to our guest panelists. Any friends paper or really cool discovery or anything you want to shout out to the audience that they should definitely see at ICLR this week? Samira.
There are definitely papers that I wanna advertise for, but I'm not prepared to do that. So yeah, I hope everybody enjoys the conference, and I hope, I don't know, we cross paths maybe in Gathertown or something, and happy to have more discussions with you.
Thanks for joining us, Samira. Rose, one last shout out from California in the early mornings. Bring me coffee. I will bring you coffee.
Sounds good. Yeah. Yeah, I'm really excited for the conference. I think I know that Noam Brown, who's another person who works in the multi-agent space, has a paper on belief modeling at inference time. So pretty relevant for people who work in you know, systems where you do have to coordinate with other agents that you only observe from the outside over some sequences of time. So definitely check out his work. Yeah.
Thanks. We didn't get to go deep into the relationship of your paper with multi-agent systems, but I kind of had a sense of it. So thanks so much for joining. Anirudh, one last shout out on work that people should definitely see at ICLR this year.
I think there are lots of interesting papers, but one thing I myself really like is actually the bootstrap meta-learning paper. And people are going to read it anyways, just because it's nominated for the outstanding paper. So not sure if that's very useful, but there are a few other papers where people have been using like forward mode auto differentiation for learning gradient updates for training deep networks, which totally gets rid of backpropagation. And I think bootstrap winter learning is just one of them. And there are a few other papers like that at ICLR this year.
All right, thanks. So we're wrapping up. We're 5 minutes past the hour, and it was such a great discussion. Time flies when you're having fun. And yeah, so more than 1,000 papers. Who knows what will be the gems of tomorrow? Sergi, I think we should compare your list with the best paper awards and see what has more impact in a year or so, or maybe 10 years, who knows.
Yeah.
Definitely future being made here, right here at this conference. And I'm really excited to dive in. So all of you, thanks. And if you're concerned, if your smartphone is spying on you, there's also a paper about that in the conference. It's called Real-Time Neural Voice Camouflage, and it tells you how to add kind of random noise to your voice so that speech recognition algorithms will not be able to understand you. So it's my tip. Thanks. And our next edition of this webinar is on May 6th, kind of the regular monthly roundup of archive and other things. And if you're interested, try our platform to navigate ICLR and discover the papers that matter most to you. Thanks.
All right. Have a nice conference.
Have a great
Thanks.
conference. Enjoy
Bye.
ICLR.
Yeah.
Thanks to Sergey and Jacob. Bye-bye.